We've already seen how functions can take parameters on their command lines. Well, it's actually possible for a shell script to also take command line parameters just like any other Unix program. So the fact is that any Unix command can receive parameters via the command line. It's just a matter of whether that program actually makes use of the parameters. Now we can make use of them if we choose to via the variables $1 through $9, and we use them exactly the same way as we use them inside a function. So theoretically there's very little new for us to learn here. We just have to see a few examples of this in use. Also, it's worth mentioning that $* and $# or $pound if you like may be used exactly the same way as well as they are used with functions, just like $1 and $9. So that essentially completes the set. Anything you could do with a function you can actually do with the shell script. So let's have a look at some examples of that. Here is a very simple script called PalmTest, which is short for parameter test, which just goes through $1, $2 and $3 and does a little if test to see if the parameter was set, and if it was, then we echo out a little message to say what it was set to, and if it wasn't, we just say that it was not set. So let's try running this program all by itself, just without any parameters first, and we find that the 3 parameters were not set. Now I'll run it again, and this time I'll provide a parameter of AAAA for the first one and BBBB for the second one. And I find, of course, that parameters 1 and 2 were set, but number 3 was not. The interesting thing about all of this is that we're just using $1, $2 and $3. We can pass any information into the script on the command line. We can pass in a file name or a sentence. A sentence can be one parameter. Let me show you an example of that. So this, and the trick is of course to put it inside double quotes or single quotes if you like. This is the first parameter, and then I don't know, anything else for the second one. Now I've got a little error message here. I was hoping I'd get this. This is actually coming from the test program. As you can see, there's a little square bracket in there where it says too many arguments. It's very easy to fix that. The problem is that I neglected to put the double quotes around that, and I've obviously got to do the same thing here. This is just one of those cases where it's vitally important that you remember to always put your double quotes around any reference to a variable when using it with the test program. So let's try that again. Well, it'd probably help if I actually saved the file. And again. And parameter number 1 is, this is the first parameter. Notice that the quotes that are in there, the double quotes that you can see after the words parameter number 1 is, those quotes were put in manually by me. They are not the quotes from the actual command line. Those quotes are removed by the shell. I'll prove that for you if you like. I'll just remove the quotes from around the $1 here, and again, and run it again, and as you can see you actually do not get the quotes from the command line as part of your parameter. Let's have a look at another example now of how we might access our command line parameters. Here is a simple shell script that uses a for loop to loop through each of the parameters on the command line and do a couple of actions there. And all we're really going to be doing is put out a little echo message saying parameter number 1 is, and then obviously the first parameter. The next line is just a little way that we can keep track of how many we're up to. So let's run that, and we'll try the old AAA BBB, and that works quite nicely. The reason I wrote this particular example is I wanted to show you what would happen if you ran a particular program like this and fed it a very large number of parameters. like /bin/star. There's all the files in the /bin directory. Now there's probably going to be quite a few of them. Let's see how many. Well, there were actually, the shell expanded that command line so that there were in fact 86 parameters on the command line. And we have, as you can see, listed all of them. So it is possible to have a large number of parameters on the command line, and furthermore it's actually possible to reference each one of them. There's obviously no such thing as $86, but there is a $8, and there's a $7 and a $9 and so forth. There's also a $*. But of course it's actually very easy for you just to go for and use a for loop to essentially loop through each parameter on the command line. And finally, I've created a little shell script here to illustrate that there is in fact a difference between the $1 and $2 inside a function and the $1 and $2 of the shell script themselves. So I've created a little function called do-nothing, and all it does is it echoes out its parameters. And then, well, that's really all the shell script does as well. So what I'll do is I'll call this shell script and I'll pass it two command line parameters, AAAA and BBBB. And when it runs, it's going to call the do-nothing function and pass it XXX and YYY. We'll have a look at what the output looks like for that. Now, the function's parameters are XXX and YYY, whereas the shell script's parameters are AAA and BBB. But both echo lines are actually referring to $1 and $2. So clearly we have a different $1 inside the function and a different $1 outside the function. So it's a very good idea not to get those confused. Probably the simplest or safest thing to do is at the beginning of your program or at the beginning of your function, copy $1 and $2 and any other variables from the command line that you're using away into other variables. Give them actual names like file name equals $1 and username equals $2 and so on. That has the benefit of actually making your shell script more readable as well. Now, this module is entitled Advanced Command Line Control. There are a few parts of command line control that we're going to have a look at, and the first one is referencing individual command line parameters beyond $9. Remember a couple of chapters ago I told you that that actually wasn't possible, that the only command line parameters that you could actually reference individually were $1, $2 all the way through to $9. Well, there is a special command that you can invoke called shift that actually allows you to reference those individual command line parameters beyond $9. It works like this. When you call the shift command just by itself, just the word shift on a line by itself, the following things happen. Whatever value you happen to have in $1 is lost. It's just gone. So if you actually wanted to use that variable, you would probably want to copy it into another variable before you call the shift option. In other words, you might say something like first equals $1. That stores the value of $1 away in the variable called first. Now, that's not the only thing that happens. $1 then is set to the value of the second parameter. So in other words, instead of $1 pointing to the first parameter, $1 now points to the second parameter, $2 points to the third parameter, and so on down to $9, which points to the 10th parameter. So you can see they've all been shifted along by 1, which is of course why the command is called shift. Let's have a look at that in action. Here's a little script called shift test, and it has a little function inside it called printPalms, which is exactly the same code as we used in one of our earlier little demonstration scripts. Now, we actually call that printPalms function and pass it $, which is every single parameter. So what that will mean is the parameters to printPalms will be exactly the same as the parameters to the shell script itself. So theoretically that will just print out all the parameters in the normal way. Then we actually run the shift command, which should get rid of the first parameter and shift all the rest along 1, and then we'll print them all out again and see what we get. So let's try that. We'll do a %, and then it's A for the first parameter, B, C. Let's see what that looks like. Okay, so initially everything looks fine. 1, 2 and 3 are A, B and C and so on, and then we shift, and now parameter number 1 points to B, and parameter 2 points to C. The original parameter 1 is gone completely. So I'm sure that you can see that it follows that if you had 10 parameters, exactly 10, then doing a shift would cause the first one to disappear and the 10th one to become $9, which would then, of course, allow it to be accessed individually. It is actually even possible to specify a numerical parameter to shift, which tells shift the number of, get this, shell script parameters that you want to shift. So I know that sounds awfully confusing, but let's have a look at what that might be. Shift 4. If you don't specify a number to the word shift, then it shifts 1. But you can actually get it to shift 4 at a time if you want. So $1 will be the old $5, and $2 will be the old $6, and so on. And $9, I guess, will be the old $13, if there was one. So there's just a handy little thing to keep in mind there. Another somewhat advanced command line parameter manipulation technique is the use of the set command. There is a command called set. It's a built-in shell command, and it's used to set the command line parameters for the shell that is currently being processing. Now, I have actually mentioned earlier that $1 through $9 are read-only, which means you can't set them individually. However, you can set them collectively using set --. This is how you might do it. You'd say set space --, space, and then you would type in the parameters that you wanted the shell to pretend to use, if you like, as command line parameters. Now, they're not real command line parameters, as you understand, but what will happen in this circumstance will be that file1.txt is put into the $1 variable, and the $2 variable gets set to Fred. You'll actually find that the set --, option is commonly used with the back quotes feature, like so. You might say set --, and then inside backwards quotes who pipe to grep Fred. Now, what that will do, of course, is if Fred is logged in, then the command line parameters of the shell will be set to the output of the who command as far as the user Fred is concerned. So in other words, there will be 5 command line parameters. One will be the username Fred, followed by the terminal name, then the month, the day, and the time, which, if you recall, is exactly what each line of the who command looks like. Let's have a look at that now. I can use that. I don't have to use it in a shell script. I can use it just on the shell's command line itself. So I could say, take the output from the ls program and make that my set of command line parameters. So let's have a look at that. We don't get any output, of course. It's just simply setting some variables. So now we might have a look at echo $. We'll have a look now at all the command line variables. Now, obviously, there wouldn't have been any command line variables before because this is a command line shell. But now, of course, we have some, and you can use exactly this technique inside a shell script. You might say, for example, echo $9, which now is just the word palm test. This technique, set --, is especially useful in setting default command line parameters, because what might happen is you might require some command line parameters for your shell script to operate successfully, and if the user actually forgets to put them in or invokes your shell script without typing them in, then you can obviously do a little test for that and say, okay, well, they didn't type in any, so let's use set --, to set some ourselves, which is very handy. Here's an example of that. This shell script is supposed to take 2 parameters. It doesn't say that anywhere, but it just is. So I might specify those 2 parameters, and I might just, the name of the script first, of course, and then mark and term 21, for example. So it says Mark is logged in on term 21. Now, if I call this script and I don't specify any parameters at all, then what it will do, as you can see, is it will take the parameters and set them from the output of the who command, pipe2 grep mvirtue. In other words, the mvirtue login details. So let's try that. mvirtue is logged in on PTS45, which I'm going to assume is correct, because $1 has now been set to mvirtue and $2 has now been set to PTS45. There's also a $3, a $4 and a $5 as well, but I didn't ask those to be echoed out. This is how I might get those to be echoed out. Is a nice little technique. I might do a shift 2 and then echo since $. Now that of course will pick up all the command line parameters, but I've actually skipped over $1 and $2, so it'll just give me $3, $4 and $5. So let's see what that looks like. And there we go, since September 5th, 1547. So there's a little demonstration of using shift with a parameter as well. There is another advanced command line parameter manipulation technique that I can show you. This one's a little more obscure than the other ones. This is all about using the IFS variable. So what's all that about? Well, when we set those command line parameters, like we saw in the last module using set minus minus, the parameters that we actually specify are separated by spaces and or tabs. Now it's actually possible to change that. We don't have to have the parameters separated by spaces. We can have them separated by anything we want. We can use the IFS variable. IFS is short for internal field separator, to designate which characters we wish to use to separate the various command line parameters. For example, we could set IFS to be the vertical bar symbol, what you might call the pipe symbol. And then, if you wanted to use set minus minus to set command line parameters, you would do it like this. Set minus minus, and then parameter 1, pipe parameter 2, pipe parameter 3. Now notice here that the space between the word parameter and the 1, and between the next parameter and the 2, and so on, is actually now no kind of special character at all. The special character is now the pipe symbol, and so $1 will get set to parameter space 1, and $2 will get set to parameter space 2, and so on. Let's have a look at a more practical example using IFS. This is a similar example to one that we saw a little earlier, where we say if there are no parameters on the command line, then we set them ourselves, and then we just simply echo out some of those parameters. Now what I'm actually going to do is I'm going to get the command line parameters from the etc password file. So the first thing I'd like to do is actually run this command line and see what it looks like. grep mvirtue / etc password. So let's do that. grep mvirtue / etc /password, and it just gives me all of the details about my login account. Now we can see there each of the parameters, or each of the fields, I guess, of that database are separated from the next by a colon. So if I actually wanted to make those $1, $2, $3, $4 and so on, then I'd actually have to use the IFS variable to designate that the colon is the character used to separate one parameter from the next. And that is, as you can see, exactly what I'm doing. IFS equals colon. So $1 is going to be my username now, and $6 is going to be, well, theoretically, my home directory. Let's see if I can't make that run. Home directory for mvirtue is /home/mvirtue. Well, that's very nice. And just for good measure, I'll echo $* and run that. And the variables are mvirtue, then x, and 3040, and so on and so on. Notice that the colons have all gone. In their place are actual spaces, which I guess just proves that the IFS variable is doing its job. Okay, that's the end of this module. We now come to usage messages. So what is a usage message? Well, the great majority of Unix commands, like ls and grep and so on, have what we call a usage message, which is simply a couple of lines of text that are displayed if the user incorrectly specifies command line parameters. In other words, if the particular command requires, say, 3 parameters and you only type in 2, then you might get back a usage message. Or if it requires exactly 1 parameter and you specify 4, again you would get a usage message. Or even if it requires a collection of options like a -p, a -j and a -k option, and you give it a -u option, again you would get a usage message. That's what they're for, and it's a good idea that all Unix programs have them. It just makes for consistency, it makes it easy for a user to quickly determine what parameters should be specified to any given command. And that includes, of course, shell scripts. So let's have a look at an example. This is the one from grep. I've just copied it exactly. Grep must be followed by some optional options. Notice that the brackets specify that a command line parameter is in fact optional. So we can have some options like the -l option or the -s option. And we can have a few of those. Then we must specify a pattern, and then we can specify 1 or 0 or more file names. File names are optional, we don't have to specify them, and if we do, we can actually specify several. So if you're about to create a script that will be used for quite some time in the future, or if you plan to release it to all of the users on your system, then you probably should create a usage message for it. And you might write code that looks something like this. If the number of parameters is less than 2, so let's assume that this particular shell script requires 2 or more parameters, then echo out usage : and then the name of your script followed by the actual 2 parameters that are mandatory, which might be a username followed by a file name. Now I've put ... there, meaning I guess that should be interpreted to mean that we can actually specify several file names. And then of course you exit the program, because there is no way to continue because the user did not specify the correct options on the command line. I've exited with the exit status of 2 there, just simply to differentiate it from any other termination condition. For example, if the program ran and it couldn't find one of those file names, then it might exit with an exit status of 1. So this is just a helpful way of saying, well, this is a different kind of error. This is an actual usage error. It doesn't have to be 2, it can be anything you like. It can even be the same. You don't even have to specify an exit status at all, but it's just handy to give your users that option. And also note that it's a good idea for this usage message to go to standard error. It is, of course, an error message, so you can do that by appending a 1 greater than &2 to the end of the echo statement. And what that means is that standard output should go to the same place as standard error is going. So that's almost it for the usage message. It's not very tricky, but there's a couple of other things that will make your usage message a lot more flexible and perhaps even more user-friendly. So let's have a look at those now. Let's imagine that we have a script called MyScript, and that it's a really useful script. It's living in some bin directory somewhere, but somebody has copied it to another location and given it a different name. So it might have been MyScript in the original place, but the second version of it might be called backup script or something like that. It could even actually be linked using a hard link, or even, I guess, even a symbolic link. So the actual same file name could have 2 different names. We could have a single script that is given 2 different names in the file system. So what are we going to do with our usage message, which actually refers to the name of the script itself? Can we still just have the word MyScript as part of the usage message? Because recall that it may not be called MyScript anymore. When we don't really want everybody who copies the script to another location, or give it a different name, to have to actually edit the script and find where we've called it MyScript and rename it to their particular name. There is in fact a much nicer solution. There is a special variable called $0. Just like $1, $2, $3 and all the way up to $9, this is actually $0, which is, if you think about it, the bit of the command line that comes before all the parameters. In other words, it's the name of the script, just as they typed it in on the command line, which of course in this case would be MyScript. So that makes it very easy for us. We can just simply replace the name of the script in the usage message with $0, giving us something like the following. Now we know that's nice and flexible now, so no matter what they call this particular file name, or no matter how many links it has, whenever they run it, the usage message will be accurate. So that's very nice. There's just a couple of things to be aware of there. $0 cannot be shifted. So you can shift things as much as you like, and the only thing that's going to change is $1 up to $9. $0 is not affected by a shift action. And it's also interesting to keep in mind that the user can often see a usage message. If you use the $0 option just like this, you can end up with usage messages that look like the following. Usage /user/local/bin/myscript, and then the rest of the usage message. Now that's probably quite accurate. If that happened to be the way they called it, they may have actually typed that in on the command line. But it doesn't make for a very user-friendly usage message. So what we tend to do is we use something called base name, which trims out everything except the very last part of the file name. In fact, it trims out all the path information. So you would end up with just, for example, MyScript, if we were looking at the following example, and the /user/local/bin/ would get trimmed out. So that last line that you can see there on this slide is a fairly generic usage message. It's got the 1 greater than &2 on the end, it's got the base name $0 inside backwards quotes in the middle, which is probably the best way that you can specify the name of the script. The only thing about it that's non-generic is the actual parameters themselves, username, file name, ... And of course they can be changed for each script. So you could just copy and paste this line from one script to the next and use it as your general purpose usage message. Okay, so that's pretty much all I want to say about that. Let's get on now and do the exercises. So here are the exercises for Chapter 9. There's 2 of them. The first one is I actually want you to write a reusable function called usage. When I say reusable, I mean this function should be able to be used with any shell script regardless of the actual parameters that that script takes. So the function should take at least one parameter, which is the name of the script. I guess you could get that from $0. And it should do the following. It should echo that script name plus any other given parameters that you specified out to standard error. It should actually beep, make a little ping noise using the Control-G character. I don't know if you remember how to do that, but it's pretty much just putting a Control-G into the echo statement. It should also echo with an exit status of 2, and we should ensure that base name is used to trim out the path information from the script name. And this is how you might call this particular usage function. It's a function recall, not a script. You might say usage and then $0, which would be obviously the script name, complete with path information if there was any specified, and then the parameters that the script should have, which would be a username and a file name, and then the ... to signify that there might be actually more than one file name required. So the usage function will actually take, in this particular example, exactly 4 parameters. The $0, username, file name, and then ... will be the 4th parameter. Like I said, it doesn't have to take 4 parameters because the usage will be different for each script that it's actually used in. Now what you could do then is you could add this usage function that you've written, this generic reusable function, to a function library, and you could call it from anywhere, from any script that you write, so you'd never have to write a usage function ever again. So that's the first exercise. And the second exercise is relating to the course project. Modify it so that it actually requires one command line parameter, which will be the name of the data file. Now this command line parameter will be not optional. They have to specify it on the command line of our script. Now obviously we need to modify the script in a few ways. I'd like you to use this new usage function that you just wrote in the last exercise to display the usage message if the user does not specify the file name parameter. And I don't mind whether you copy and paste the code from the usage function into your course project, or whether you use the dot operator to include your function library that contains the usage function. Now, if they specify a file and the file exists, you must check that you can write to the file. If you can't write to the file, then obviously the database isn't going to be able to do its job, so we exit the program with the appropriate error message. If they specify a file and the file does not exist, ask them if they want to create the file. And if they say no, well, there's nothing we can do really, because they don't want to create a file, so we must exit. Now, if they say that we can create the file, then create it, of course, and then check that you were able to create it, because obviously whatever you did to create the file may have failed, and if it failed, obviously you'd have to exit at that point. So the only way that we'd actually make it through to the rest of the bulk of the program is either if the file exists and it's writable, or the file does not exist and we were successfully able to create it. Okay, so there's a little bit of work for you to do there. It's all good practice. These sort of techniques are very common. So good luck, and I'll see you in the next module where I'll show you. Okay, so how did you go? Here are the solutions to the exercises from Chapter 9. Okay, so here's my solution to the first of those two questions about the usage message. And this script is actually called usage message, and it is available, of course, on the CD in the Chapter 9 folder. So here's the little function itself. Now the very first thing I do, and this is the only clever part of the whole script, is I take $1, which is supposed to represent the script name, and I store it in a little variable called script, and then I shift. I skip over that, so now, after I've shifted, $*, represents all the other parameters, however many there happen to be. There may be none, or there may be 20, it doesn't really matter. The point is, now I can use $* to represent all the other parameters. Now why have I done that? Well, the reason I've done that is essentially so that I can just do a base name on the first parameter whilst leaving all the other parameters alone. And that's exactly what I've done. So then you can see I've echoed the output to standard error. I've put in a little Control G, which is not just a caret followed by a capital G. You've actually got to type Control G on the VI keyboard as you're editing the script if you want the Control G character to be put in at that particular point. And after that it's pretty much satisfactory, straightforward. Just exit with the exit status of 2. So let's see if that works now. We'll just pass that 3 parameters. This is the example that I showed you before in the place where I actually specified the question. Let's run this, and %. And the usage message is, well, usage_msg, file name, username ... And I actually heard a little bing there, a little bell, which you probably didn't hear, but I did hear it. And just to test that the base name is working, let's try that again. Let's say $%. So that'll be $usage message, and hopefully the base name part will strip out the $, and it should still work. And it did. There's no $/ in that usage message. Okay, so it's fairly straightforward. The trickiest part was that little shift to separate out the script name from the rest of the parameters. Let's now have a look at the course project. So let's have a look at the changes here. The first change is the actual addition of the usage message, and there it is, fully commented. So that's simple enough. And now I'll scroll down a bit and find the actual start of the main code, which is here. Now, here is where we do the test of the command line parameters. Did we get exactly one parameter? Does $# equal 1? Now, if that is false, then it will run usage $0 file name. So the very first thing I'm going to do is actually test that. I'll run it as follows, and this time I'll specify no parameters on the command line just to see if that works. And yep, there we go, there's the usage message, just as you would hope. And I would also hopefully get that usage message if I specified 2 parameters on the command line. And again, I do. So, if we got to the next line, then we actually must have supplied a file name on the command line. So let's store that away. I'm going to store that in the variable called fname, and I will really not need to refer to $1 anymore for the rest of the script. So let's see if it actually exists. I'll use the -f to check whether A, it exists, and B, it's a regular file. So first, if it does not exist, we'll echo out a message to that effect, and then we'll ask them if they can create it, and we'll handily use that yes/no function that we used earlier. And if they say yes, then we'll create it, and we also need to check that that's succeeded. So now the file should exist and it should be writable, and if it's not, then we need to put out a message to that effect saying we couldn't create the file and exit the program, and otherwise we're okay. But there's still a couple of other cases to check, like they might have said no, they don't want to create it, so we'll go in here and we'll just exit. It's not an error, it's just they've chosen not to proceed. And this else, or this elif if you like, that was connected to this original if statement here, where we checked whether the file existed or not, and we went into this first case if it didn't exist. So now if we get down to here, then the file did exist. Now we can check that it's writable, and if it's not writable, then we put out a message to that effect and exit. And of course, if it is writable, then we can just proceed onwards, and we get down to the rest of it, which is right here. So let's test that. I will run it, and I will specify a file name. I'll just call it test.dat. Now I didn't really test it, obviously. I'll try that again. Specify %, which is the current script. Test.dat. Okay, here we go. Test.dat does not exist, which is correct. Create it. No. Okay, so let's try it again, and this time I'll say create it. Yes, we will create it. And here we are ready to go. It must have successfully created, otherwise I wouldn't have got this far. So let's create a record, and we'll just specify some rubbish in here, and those details are correct. Create another record, no, and view the records. Yes, there they are, aren't they lovely? Okay, and quit. And yes, I really do wish to quit. And now when I run it, it should not tell me that the file doesn't exist, because the file does exist, and it just goes straight in with the file name that I specified, ready to manipulate the database. Now I did actually specify a file name then. I know that I only went hang on, let's get out of this. I know that I only went like that, $! But what that really was doing was $test.dat. That's just repeating the last command, as you recall. And recall, of course, again, that the % is just the name of the current file that Vi is editing, which is the script, of course. Okay, so that's it. It works. How did you go? Did you get a working script then? I hope so. Okay, we've only got one chapter left in the whole course, and then we're done. Let's move on.